it's a hard task, but it can be accomplished through the various engagements from the various companies, utilities, the infrastructure management people, and all of them. But the Paris Agreement, what it is saying is that the global warming potential, especially the rise in the global temperature, the average temperature, it has to be limited to 1.5 degrees Celsius than the pre-industrial levels. So that is the main objective of that Paris Climate Agreement. It is the outcome of that one. And first it was 2 degrees Celsius, and later on they agreed to be in 1.5 degrees Celsius rise. So because of that, most of the countries were going to the net zero emission control strategies. So in this presentation, I will be going with some global updates on the hydrogen and its applications, then the renewable energy and hydrogen updates. Then we will see with a case study in Oman how a feasibility analysis can be done for a hybrid energy system, especially governing with the hydrogen. Then I will be concluding the sessions with certain remarks on that feasibility analysis. Afterwards, I will be explaining you certain future directions in which the green hydrogen can take forward. And finally, the discussions. So related to the hydrogen benefits, so this is a very elaborated topic, and most of them deal also with this hydrogen benefits. See, generally the hydrogen which is available is not of any color. But presently, in our context, we are keeping certain color coding for that hydrogen. It is just to distinguish what is the type of manufacturing and what is the procedure which they are following generally. First of all, they are taking as gray hydrogen. The gray hydrogen means this is the very conventional method of generating the hydrogen. It is through the steam methane reforming. See there, the natural gas or the coal or any conventional fuels they will be using, and from that they will be generating that steam, and with the steam, the hydrogen also will be coming out from that. So that is that procedure of SMR, and through that, a huge carbon dioxide emission is happening. So if that carbon dioxide emission is there, obviously we know that we cannot count it as a green. So obviously that is going to be a gray hydrogen. But later on with the new techniques of carbon capturing schemes, what they taken further is SMRs, which they are contributing the hydrogen generation. They incorporated the carbon capturing schemes. See, it is called a CCUS in carbon capturing, utilization, and storage. So this technology, if it is incorporated to the hydrogen generation strategies, such generated hydrogen we will be calling as blue hydrogen. And the last one, obviously we know that the if you want to call a hydrogen as a green, if it should not contribute any carbon dioxide emission as such. So that's why when we are doing an electrolysis just with the water, and by giving the DC electricity, you can do that electrolysis, and finally the outcome will be the hydrogen as well as the oxygen. So this is the very green way of generating this hydrogen. Now this hydrogen which is coming out from this electrolytic process, it's a very pure hydrogen with certain water content, moisture content. But other than that, it is the most purest form of that hydrogen we will be getting. See, if you are seeing the benefits of this one, it can be produced without any carbon footprint. Can be transported over a long distances as a gas or as a liquid. It has a high energy density when it is compressing as a gas, and it produces very clean power and it can act as a fuel too. And it's a clean industrial feedstock. Industrial feedstock means, see, it is not only with the power generation, it can contribute to the heating, industrial processes, and other things. So it's a very clean industrial feedstock, we can call. And the versatility as an energy vector is also widely accepted nowadays. And first of all, it was introduced with certain automobiles. Now in the power sector also, it is coming with the fuel cell, emergence of the fuel cell. The safety considerations, it is one of the burning topic we have to deal with. When the hydrogen is there, it's highly flammable. So the thing is, we have to follow the safety considerations, and it is almost similar to that of the natural gas or the petroleum products which we are dealing with now. Now, sector-wise application, if you are asking, actually the hydrogen is can be dealt with for the feedstock applications as well as the energy applications. So, as I mentioned before, it can be taken to the industrial process, just like petroleum refining, ammonia and methanol synthesis, or the steel production. So that is the industrial process generally utilizing this hydrogen. Another the sector, as I mentioned, it's the power generation sector. It can be used as a flexible power generation. It can be used as a off-grid power supply. And for the large scale energy storage also, hydrogen can be a medium. In addition to this one, it can be converted to certain synthetic fuels, then ammonia, that is giving that flexibility. Then heating, industrial heating, as I mentioned before, that for the residential heating, especially in the European countries, it can be an option. And in the transport, as you may be aware of, fuel cell cars are getting available, and it is having almost a competition with the battery operated electric cars currently. And this is all the happenings. To agree for the Paris Agreement, according to this 1.5 scenario, by 2050, the hydrogen and derivatives has to account to almost 12% of the total energy usage in the worldwide. And out of that, it is expected to be the 2/3 of that hydrogen has to come out from the green way, that is the green hydrogen. This is the 2021 IRENA report is saying about this. So that is showing the importance of that green hydrogen as well as the hydrogen in the market. Now, this is in a broader perspective. So just we can see the different hydrogen applications in as a whole. Why? Because you might have heard about the hydrogen economy. This terminology is coming because the hydrogen can be a fuel and it can govern the total economy of that particular state or a region. So it is doing by keeping this hydrogen as the main fuel, and it is distributed with the various applications. For example, centrally the electrolysis plants has to be there, electrolyzers has to be there, and that has to generate that hydrogen. And there should be a supply chain of the water facility, it should be there, a logistics should be there. And after the generation, it can be taken as the gaseous storage or the liquid storage or as a solid storage. It's possible, and it can be taken through the tanks and through the gas pipelines also, that transportation can be. And the buses, the hydrogen buses are one of the application of the hydrogen. Then the vessels, especially in the seaside, the vessels. Then you can see here the trains which is running with the hydrogen, and the hydrogen blending with the natural gas. And in addition to this, there is one more thing which we need to note down. Presently, the bio wastes, that bio waste also we can do the reforming and can convert into the hydrogen. So that is another possibility. Especially the municipal solid waste, the bio waste, all these things we can do the methane reforming, and we can convert that to the hydrogen. That is another possibility. Now, related to the latest statistics, what it is saying is that, especially the renewable side, photovoltaics are leading the renewable components, especially in the generation side. And wind, especially in that particular locations, which is having an average wind speed of above 5 meters per second, it is giving a potential. And that's why the wind is the second component, and onshore and offshore wind possibilities are there. But you can see here from the statistics that by 25 to 30, that in 5 years, the increase which we need to make is almost a double. Double the present installation capacity, we need to make that installations. So that is the task ahead. And related to hydrogen also, it is expected to be, the improvement is happening in the hydrogen side. So low emission hydrogen, when I'm saying about the low emission hydrogen, I'm including the electrolytic hydrogen as well as the hydrogen which is coming out from the steam methane refining, especially with the carbon capturing schemes. So that is that CCUS. So you can see here the from the statistics that, see here, the component of the hydrogen which was there in the 2021, it was for just 0.6. So it's in the metric million tons per annum. So this was the in 2021. In 2022, it raised to 0.7 million tons of tons per annum. Now in 2025, it is reaching 1 million metric tons per annum. So this is the growth rate. The growth rate, if you are silently observing, you can see one more thing. See this green side. The green side is especially the electrolytic hydrogen. This electrolytic hydrogen's ratio is also increasing. And at the same time, when we want this hydrogen, we need to increase the installed capacity of that electrolyzer. So the gigawatt capacities of the electrolyzer is also increasing gradually, and it is now currently reaching almost 9 times. And similarly, the electrolyzer manufacturing capacity also to be increased, and that is growing at a little bit slower pace, but it is also reaching almost 57 gigawatt per year. Now, when it is coming to India's, if you want to attain the net zero emission objectives by 2070, we need to have our primary energy supply through almost 73% of the primary energy supply should be generated from the zero carbon sources, just for example, the renewable energy sources. So that is what the main objective. And once when we are starting the statistics from 2022, why? Because in 2023, actually, we agreed upon for the 2070 net zero emission objectives. So that's why the statistics are starting from 2022. And as you can see in that chart, here 30 exajoules was the total energy consumption. But if you are coming to the 2070, this energy consumption will be high. But the thing is, if you want to be in the safe side of 2070 attaining the target, you need to be 45 exajoules consumption. So that is the consumption rate. It has to be a maximum. So same like that, you can see here the carbon dioxide emissions which is happening. Carbon dioxide emissions in 2022, if you are observing, it will be 2.6 billion tons of carbon dioxide. And that once when it is coming to 2070, it has to be reduced to 0.8 billion tons. That is the target which we need to achieve through the various strategies which we can adopt. So here, based on that, 2023, Indian Parliament and Indian government actually approves a national green hydrogen mission, and they targeted to finish almost 60 to 100 gigawatts of electrolyzer capacity by 2030, and which will be aiming at a production of 5 million metric tons of green hydrogen annually. And the transmission networks also need to be made, and the renewable energy capacity also need to be made. And for that, the renewable energy installed capacity, it has to be raised to 125 gigawatts. Similarly, Oman also is having certain net zero objectives, and their target is a little bit early. India is targeting for the net zero emission by 2070, but Oman is targeting to keep it by 2050. This is also a little bit optimistic target fixing, but yet the country is trying for it. Presently, if you are observing, the majority of the power generation as well as the energy consumption, it is completely from the fossil fuels, as it's available in plenty in this region. So they want to be as the largest exporter of hydrogen in the Middle East. That is their aim, and that is almost by the announced project of 2022 from the IEA's, International Energy Agency's global assessment. They are saying that Oman can be a key player in that hydrogen. And the set targets of the country is to at least 1 million tons of renewable hydrogen to be generated by 2030. And it has to be gradually increased to 3.75 metric tons, million metric tons, and 8.5 million metric tons by 2050. So that is the country's target. So here the expected capital cost reduction of 70%, cost of production, producing the renewable energy hydrogen in Oman. See, when here the capital cost is reducing, especially in the components manufacturing. So if a 70% reduction is happening, at that time, the cost of the renewable energy hydrogen can be $1.6 per kg. That is a projected estimation with a condition that 70% capital cost reduction has to be there. Then only we can achieve the $1.6 per kg hydrogen. So now I'm coming to a case study of Oman. So here, most available options of the renewable energy is photovoltaic and wind. And the photovoltaics is having a good potential here. Why? Because it's almost 800 watt per meter square. You can get that autonomy for almost 8 hours in a day. But there are some disadvantages also. Disadvantages in the sense that, for example, the dust is among the highest. And another thing, the cell temperature is also very high, especially here. So especially in the summer, the temperature may be going up to 55 degrees Celsius, and that is affecting the photovoltaic installations too. So it's having pros as well as cons, we can say. So now the objective of this feasibility analysis was to find the most favorable location in Oman for this PV wind hybrid system. And another objective is that to check whether we can have a partial replacement or a complete replacement of the conventional generation, and an optimal sizing for the hybrid energy system for that particular location. Then to estimate the greenhouse gas emission reduction possibility. And finally, we need to know how much is the renewable energy penetration exactly can be done to the grid system by considering the reliability constraints. So here the main objective is to maximize the GHG emission reduction and obtaining a optimized system. So the location what I selected for this study is these three. Dhofar region, especially you might have heard about this region as Salala. So when I gone through this three locations, what I found the latitude and longitude we are having. And once when we are taking this longitude and latitude of these zones, and if you are giving it we can take in two ways, the meteorological data, direct measurement is possible. Otherwise, the NASA's web data is giving a very clear picture of about the irradiance as well as the wind speed in these regions. So I taken both the things, and it is almost the comparative results I was getting in both the cases. So what you are seeing here is the irradiance data as well as the wind speed data of these three locations for the complete 12 months in that year. So we can see that the highest solar irradiance is happening especially in the Dhofar region, and at the same time even the wind speed is also is high in that Dhofar region. So in the further analysis, what I taken is, I taken the most favorable location. I just go forward with that analysis. So here, after considering that particular locations, I just taken the loads, the electrical load and the hydrogen load. The hydrogen load, what I taken is, it is 11.27 kg per day. It's a very small size system. And the electrical load also, it is a very small system of 24.57 kilowatt. It is including the electrical particular residential load. And when I analyze the load, the average energy consumption of that electrical side, it is coming as 165.24 kilowatt hour per day with a load factor of 0.28. And the hydrogen load, it was 11.27 kg per day, as I mentioned. It is sufficient hydrogen for filling two automobile cars, especially. Here we check that one. We are having a fuel cell car called as Toyota Mirai, and it is almost 5 kg is the full tank, and that means that almost 2 full tanks we can make in a day. So that is the hydrogen load we considered. So for the analysis, the tool which I used is a software called as Homer Pro, and it is developed by the National Renewable Energy Laboratory of US, and presently it is acquired by the UL, Underwriters Laboratory. This Homer Pro is recognized as a global tool for optimizing the micro grid design. The main features of this Homer Pro is that it can do the optimization of the hybrid systems, and it can do the simulation of that hybrid system which you model. Then the sensitivity analysis of the parameters which you want to have, that is also is possible. Then the cost analysis of that hybrid combination, we can do it. The emission analysis of that hybrid system which you are modeling, that can be done. And finally, the risk analysis. So once when it is feasible, which component is creating more risk, that also we can identify, and how much risk it can happen. All these things we can analyze using this software. Now, Homer is having its own inbuilt optimization algorithms. And in addition, if you want to do certain algorithms, that is also possible by linking the MATLAB to that one, to the Homer. So here, for this analysis, I adopted a cycle charging as well as the load following algorithm, which is an inbuilt in the Homer. So this is the, on the right hand side, you are seeing that flowchart, how I did that one. So we need to give the technical inputs, then meteorological data and the financial inputs for that particular location. Then we, what are the components we need, especially in the power generation side, that has to be modeled. And that is the energy generation model which we have to create. And at the same time, you need to have a load model. That load profile we need to have. What is the type of load and what is the capacity you need, what is the ratings you need, all these things you need to keep it there as the load profile. And afterwards, when you are having this energy generation model, you can try with the different hybrid combinations. Once you made that energy model with the different hybrid combinations, this Homer can check that feasibility. So when you are, when the feasibility is calculating, it is based on the energy balance calculation. Whether it is the cycle charging or the load following, both are running based on the energy balance calculation. But the cycle charging, in addition to the load following, what the advantage is that if you are having any excess energy, that excess energy, it can be given to any other load, just like a deferred load or hydrogen or any other type of loads. So once when this is covered, that it will be calculating all the financial parameters, just like net present cost, levelized cost of energy, the carbon dioxide emissions, and the simple payback comparing to the base case which you are taking. Base case, normally what we will be taking is the conventional generation which is available in that particular zone. That will be the base. And whatever be the hybrid system combination, that will be coming as the proposed case. So the comparing to this one, the base case and the proposed case, it will be giving the payback. So that is the advantage of that system. And the finalized feasible combination, it will be giving based on the maximization of the renewable energy fraction. That's the how much it can penetrate to the grid. And second one, the return on investment, then the internal rate of return, the minimization of that NPC, LCOE, CO2 emission, simple payback, and LCOH if the hydrogen is involved. And after that, that cyclic algorithm, when once it is run, we will be getting the optimal sized system. So as I told before, in the Homer Pro, we can prepare the hybrid energy systems. As you can see here, I made a system with the diesel generator as the base option, and the remaining, the wind turbine, photovoltaics, battery bank, and the converter. This is the renewable energy combinations I made, and together with that one, I connected from the DC grid this electrolyzer, and that hydrogen circuit, it will be forming it here, and the hydrogen which is forming there will be stored in the hydrogen tank, and it can be dispersed through the hydrogen fueling stations. So that is the way. Or if you want to transport it, that is also is possible. And here the electrolyzer component. So here we need to define what are the type, what are the specifications of each type, each component which we are giving it there. So here are the specifications I entered into it. So the diesel generator, photovoltaics, the battery, wind turbine, electrolyzer, inverter, all these specifications we can enter into the system to create the energy model. In addition to that one, we need to give the financial inputs of the to the model. Why? Because we need to do the financial analysis. So each component, the diesel generator, I kept the capital cost as $250 per kilowatt. So how much kilowatt it is using, the rating which you are using. So based on that, that capital cost will be taking into in the model. And similarly for the photovoltaics also, we need to give the capital cost, the replacement cost, and the operation and maintenance cost. So these are the costs I am giving. The cost we can give in two ways. One is from the existing market, what is the available prices, or from the existing case studies if you are having, that one you can use. Otherwise from the literature we have to take. So I depend in both the cases. I checked the both literature cases as well as the existing one. It was found very similar, and that's why I used that one. Especially from the literature from this region will be giving more close values of the reality. Now, as I told to you, the various combinations I tried is first one, the base case of diesel generator alone. Second one, the wind and diesel generator, then wind and battery and DG, photovoltaics, wind, battery and DG, photovoltaic and DG, PV, wind, DG. So 9 combinations I found that it is almost feasible. So the electrolyzer tank, the capacity what I taken is 38 kilowatt that you can see from here, and the hydrogen tank which I opted is of 55 kg the capacity. So when I run this simulation, what we can find out the optimized sizing rate of each cases. Whether it is a PV, wind, or DG, or battery, or inverter, we can keep it for the Homer optimizer and can get that values. In two ways we can do. We can do it as a Homer optimizer, or otherwise we can define that values and we can keep it fixed and then check the feasibility. Both the possibilities it is there in the Homer. So here we can keep four components in the optimizer, and the remaining thing we have to define. So that is what the option. If you don't want to optimize by the Homer, and if you can define the things, that is also fine. So here I opted for the Homer optimizer in this case. Why? Because I need to know whether this system will be feasible and whether the Homer can give the optimized results on it. So this is the results the specific sizing I got from this Homer. And afterwards, I did that energy analysis. And in that energy analysis, as you can see here in the screen, the main thing what I observed is the last two. So here you can see the energy generation from all the sources to meet that particular peak demand. And here you can see that if you are having the DG alone system, the excess energy was very less. And the renewable energy fraction is 0. And the total energy generation was from the source to from the DG to meet that load. But in the other cases, if you are seeing, especially for the second case, if you are seeing wind and DG, the renewable energy fraction was high, that is 81.3. That means the wind was contributing more than the DG. But at the same time, you are having that excess energy. The excess energy means the surplus energy which is coming into the system. Once if a load is there and the source will be generating a little bit more than what is required for that load. So that is counted as the excess energy. So this much excess energy was there in the system. This can be utilized for certain purposes. it can be utilized for the hydrogen generation. Okay, here we are having this hydrogen generation, and if you are opting it for the optimizing of that one, it will reduce. This excess energy will be reducing. So that you can see. And another thing, we can use any deferred loads. We can use any heating loads. We can use it again. The fuel cells we can use and can generate another form of energy. These are all the possibilities of reducing this excess energy. But now in the system, what I am having, I put these particular combinations and observe that excess energy as well as the renewable energy fraction. One important thing what you can see from this this table is that as the renewable energy fraction is increasing, you can see that the excess energy is also high, especially. But when I am using this hydrogen system, and especially I am combining with the battery, that systems are generally having the excess energy less. So that you can observe in the case number cases with the batteries. But if you are combining these two battery sources, sorry, no, not battery, energy storage sources, generally the excess energy will be coming down. That is observed in the this analysis. Now, when you are observing the financial analysis of all these cases, what we can see is the case number 5, which we have to note, the levelized cost of energy. How much is the dollar which will be coming per unit of generation? It is LCOE means don't take it just like a cost of energy. It is taking as a cost of energy, but in a broader perspective, in the sense that it will be considering the total lifetime of that particular project, and in that lifetime, whether it's if there is any replacement required, if there is any operation and maintenance cost, all these costs it will be considering, and it will be giving that particular parameter, so parameter of levelized cost of energy. So it is a very comprehensive value which we will be getting there, and that will be almost the that is a parameter, the marked parameter which can be taken it for the cost fixation. So you can see here the case number 4 and 5. The 5 is the lowest which is having the LCOE, and here if you are observing these things, the IRR and ROI, the rate of return as well as the IRR. These two are the financial parameters. If it is high, that project will be more feasible. So in this case, we can see that the case number 5, this is high, especially for the IRR and ROI. And the LCOE is really low. So this is giving an indication that the case number 5 can be a very feasible combination. And especially when you are coming to the emission analysis also, we are seeing that comparatively the carbon dioxide emissions, the carbon monoxide emissions, sulfur dioxide emissions, NOx emissions, unburned hydrocarbon and particulate matter. These are the emission contaminants, especially it is calculating. For the case 5, comparatively, it is low. And the renewable energy fraction, if you are seeing, it is close to 85, that you can observe in the in this case. So this is the renewable energy fraction is 85, and at the same time, it is having a good IRR, good ROI, and lowest levelized cost of energy. This is giving an indication that this case 5 is a better combination among all other. And it is significantly reducing the 97% of carbon dioxide and carbon monoxide of 99% carbon monoxide it is reducing from comparing to the base case I am telling. And 98% of sulfur dioxide emission it's reducing, and NOx emission also it is reducing 98%. So this seems that this giving an indication that this case number 5, that combination can be a well fit for this particular case. So this is what I put forward in this one, and the LCOE of the system for meeting the energy demand is 0.4 to 1, and the level is cost of hydrogen which was getting from this project. It was of the rate $4.65 per kg. This is a very reasonable LCOH in this region, and I compared it with the various LCOHs which we were receiving from the various zones in this Oman. That is all compatible, and it is saying that these results are on par with the analysis which they are doing. Now, this is the paper which I published in 2025, actually in the January. This is available in the Springer Nature, that is in the interactions. So now from this one, I am taking forward to the future directions and initiatives which we can. The future directions and initiatives in the green hydrogen, especially all over India, they identified 17 particular locations in which they can go for this green hydrogen. And as I mentioned before, it will be starting from some pilot projects, then it will be moving to hydrogen values, and later on, it will be moving towards a hydrogen ecosystem in a very broader perspective. So this is a document which I got it very recently, and it's Kerala Green Hydrogen Valley Vision 2040. This is comprehensively giving the ideas how a hydrogen valley it can be, and what are the components and how this can be incorporated. See, some of the issues are also there in the green hydrogen that I will discuss in the after telling about these particular points. So before we will see the Vision 2040 of Kerala Green Hydrogen Valley. Here they are trying to make the especially as I mentioned before, the hydrogen, they will be using it for the industrial process. In Kerala, what they are targeting is 120 kilotons per annum consumption. It is possibility is there in the industries. So the main point of location will be in Cochin, and they are having the water metro, then the fertilizer unit is there, FACT. Then the green ammonia exporting possibility they are checking. They are checking the KSRTC buses with the hydrogen fuel, the water metro. These all possibilities they are seeing, and the ammonia bunkering to the ships, the exporting through the Vilnius harbor. All these possibilities they are seeing, and for this one, they need to make a huge infrastructure, and the infrastructural changes also to be done in certain aspects. But they are having this vision for 2040. So that is what I understood from the document. It is released by ANAT. It is available in the website. Now, another problem which is there in the power sector, I just want to address, and you people also can go into this one. You can see this problem in the newspapers. I saw this one in the Madhubhumi as well as in Kaumadi. What it was saying is that presently the rooftop installations, the KSEB was giving that the monetary benefits to the people, right? So with that one, huge installations started coming in most of the parts in Kerala. After that, what they found is that the power from the photovoltaics, it will be there in the peak during the daytime. But in the night time, that is the peak time in which the grid needs the power, especially from 6 p.m. to 11 p.m. And during that time, they are not getting the power from this. So they have to give it to the houses. So this problem, it was there. And finally, they were coming up with some ideas that those who are having the rooftop solar power, they should have the battery backup too. So this is a temporary solution, I feel. But the surplus power which is coming in the grid, it can create so many other issues, just like the high voltage increases in the system, the temporary failures in the systems, the unwanted heatings in the systems, then even can affect the grid parameters sometimes. These all possibilities are there. So from the green hydrogen, can we come up with a solution? So this is what the question which I just want to throw it to you. The thing is, what I found from the literature is that there is a possibility. So the battery can be a short-term storage, and in addition to that one, if it is coming as the excess energy from the, especially the renewable energy, it can be stored in the form of a hydrogen. But what is the possibility, how it has to be taken, and how it has to be taken to the planners and the economists? That is a broad problem. It has to be solved. So this is what my presentation it is going to be. And my references what I taken for the case study as well as for this analysis, I am keeping it here. And thank you. And I'm welcoming you all for the discussions. Hello. Hello.
Wait a minute, sir. Hello, sir. Ansel has raised the hand. Please ask the question, sir.
Hello, sir. Am I audible now?
Yes, sir.
Yes.
Sir, actually, sir, regarding the hydrogen valley, sir, but yeah, I think for the past few years we have been discussing for this hydrogen valley projects and everything, sir. But still, what we are facing is the system integration part, sir, and that's my first one query, because till now we are not able to have a clear picture how to address this issue. And second one, sir, when you were discussing about the emission analysis part, so you told the best result was when you're giving a combination with DG, right?
Yes.
Like PV, wind, and DG. So, but still, when you're looking on your normal human being, like not on the technical side, when you're looking for a general social perspective, the usage of these DG is always considered as emission equipment. So that will be a contradictory, right? So that findings. So I would like to clarify. That's my second question.
Correct. See, your question, I will answer from the second question. The second question is saying about the contradiction with the DG sets. So the DG sets actually, as you can see, even though the DG is using the 85 to 86% of the power which is penetrating is from the renewable sources itself. That means to ensure the reliability of the system, we are using this DG as the backup there. So that is in case of any emergencies at that time, if there is any peaking of the loads or any other things which is happening, during that time only the DG has to act. So why? Because you know the intermittency of the renewable energy sources. So we cannot ensure that this all the time the load will be met. So that's why, to ensure that the unmet conditions are not there, the reliability constraint also we need to see. That's why that DG sets we are just incorporating as a part of it. So it is, as I mentioned in my aim, It is not saying that the DGCET or the natural gas combined cycle power plants should not be there. It can be there, but should be as a backup, which will not be giving a it will not be the major part playing there. It has to be the renewable energy. So that is what my first point, my answer to your second question. And my first question, that infrastructural changes, so many things to be done. It is just a plan. The valley, the hydrogen valley is just a plan. This was drafted by the ANAR as a project, and there is a possibility of doing this one, but it needs so many infrastructural changes, the sanctionings, so many things, land, the water availability, all these things are the part of that. They are having certain proposed activities also in that plan. If you are seeing, that document, you can see what are the things they are planning for it. But I know still it's so many red tape issues are there in that.
Participants can open up your doubts here.
If participants have any more questions to ask, they can post their questions in the chat box or unmute.
Sir, why are we always, I have seen all of your papers that you have always used a Homer software for optimization and other calculations. Is there any peculiar benefits for this Homer software, sir? Are there any other open softwares available for us to work on?
It's a good question, actually, related to the research. Most of the feasibility studies related to the hybrid energy systems, there are certain softwares available. And if you are seeing the softwares, I can name some of the things. For example, one is renewable energy technology screen. It is called as red screen. This is one software. And another one, you can see SAM, system advisory model. Then another one, most of the softwares are released by NREL or especially some good agencies. And each tool is having, we need to treat these softwares as just a tool. If you want to do certain analysis, you need to take a tool. So if the tool is having that particular options to complete that task, yes, you can opt for it. Otherwise, you need to search for some other tool which can be feasible to that one. In my case, what I selected is this Homer tool. Why? Because the projects which I am interested is mostly with the hybrid energy systems. So hybrid energy systems, it is very easy to model in this Homer. So that's why I opted for the Homer. The same thing, it can be done with the MATLAB. MATLAB, you need, see, this is not that as difficult as that of MATLAB in creating the systems. So that's why I opted for the Homer. It's Homer itself is having so many negatives, but what I found is that especially when the research papers, if you are going through the research papers, the wide range of applications, for the wide range of applications, especially in the hybrid energy systems, this software was used, and it was widely accepted in the that scenario, research scenario. So that's why I opted for the Homer.
Okay, sir. Thank you. Sir, one more question has been come up. Which country is leading in green hydrogen sector?
Presently, of course, China, I can say. Why? Because the capacity of electrolyzer, they are increasing like anything. It's in gigawatts. So that China is leading that technology also, especially in the electrolyzers. But India is also becoming a key player in our region, and in the Middle East region also, so many competition is going on, especially in the Saudi Arabia, the UAE, and Oman. See, you can see, compare that one, which one is performing well, by taking the levelized cost of hydrogen in that particular region. So levelized cost of hydrogen, if you are taking for each region, you can understand. See, sometimes they are having a cheaper technology and they are having a proper, well structured supply chain. Then their levelized cost of hydrogen will be low. But if some of the countries, they are not having the supply chain of that one, and a lot of countries presently, if you are observing, so many hydrogen projects are cancelling. Why? Because the demand is not there sometimes, proper infrastructure is not made, then the supply chain is not there. So these all are contributing to the cancellation of the hydrogen projects in countries, including US.